The exponential probability distribution deals with questions under the right circumstances for processes that follow all the rules of a Poisson process. We've talked about that in a different screencast. But if you have a situation that follows the Poisson rules and you say, well, how long am I going to have to wait until she calls me back? Then the exponential probability distribution is the go-to distribution. The distribution itself, its PDF, is governed by one single parameter, and it's the same parameter that we saw with Poisson. It's lambda. It is the long-run average rate of occurrence. And so the PDF is lambda over e to the lambda t. Frequently, you see it written as lambda times e to the negative lambda t. What's going on there is, just remember, when you have a negative exponent, it's saying take the reciprocal. So they're just equivalent ways of writing the same basic reality. All right, let's get to the juicy stuff. I'll cut to the chase. All of this table, what it really does is it helps us to populate tables that we've built out for you. So I'm not going to spend a lot of time on those. What you do as a user is you put in your value for lambda. That is your one single parameter, and it's really important. Let's make a couple observations together. First of all, I'm going to pick a lambda of 2. Look at the y-axis. The y-intercept is at 2. It is always at lambda. You can look at an exponential distribution, and within reason, as long as it's got good labels and everything, you can see what lambda is just by what the y-intercept is. The other thing that I want you to pay attention to is that as lambda goes up, we collapse. Our PDF curve collapses towards 0 faster. So notice here we're at 0, 0.5, 1, 1.5. If I take this from 2 up to, say, 5, we're moving down very rapidly now, right? Like at the 0.5, we're quite low. And our y-intercept, well, it's now at 5. If I go with a lambda value that's, say, 0.75, now I have x values at 5. I've got 10, I got 15. We just weren't seeing that before, right? Like if I put it at 5, we're basically collapsed and zeroed out at 1.5. The lower the lambda, the more values that we can entertain as being quite likely. That's something that I want you to observe, and then we'll just go with 1. Kind of interesting. Here we have a shaded region and saying like, well, what's the probability that we would land between 0 and 0.33? If we think of these as units of time, then a third of a unit would be 20 minutes. So what's the probability that we would see something, the event of interest, occur within the first 20 minutes between 0 and 0.33? Well, it is a 0.28 chance. That's what that is. We could go and say, well, what about 0.2 to 0.8? And that would give us this set of values here. There's a visualization. And then finally, we have the PDF in Peach. Technically, this isn't quite right because they're columns. You're not supposed to have columns for a continuous distribution, but it's a nice visualization and it's not going to cause you any mathematical or statistical harm. And then we have the associated CDF. And really, a PDF kind of gradually slopes down and out towards 0, and its corresponding CDF always goes up and then levels off towards 1. That's the pattern that you're always going to see. The last thing that I want to draw your attention to is you can head on in and hit any of the values that are in orange once you've made a copy of the file. And so if we asked you, hey, given an average of 1 hour waiting time, what's the probability that you will wait 0.75 hours or 45 minutes or less? What you would do is you would just put in 3/4 of an hour, 45 minutes is 0.75. And I am going to have an associated probability of 0.528. Or if we asked you, what's the likelihood that you're going to have to wait anywhere between a half an hour and an hour and a half? Well, there is a 0.383 chance that you are going to have to wait somewhere between half an hour and an hour and a half. So that's how this tool works for you. And yeah, we hope this is helpful.